Thank you for joining us for episode 11 of our Gleeble webinar series. This webinar aired originally on July 9th, 2020. During the presentation, we did have some technical difficulties with audio, so we have re-recorded the presentation. We hope you enjoy it. My name is Daniel Quigley. I'm the Director of Business Development and Marketing here at DSI. This is our 11th webinar in 11 weeks. Many of you have been here for all or many of these sessions. Some of you may be joining for the first time. Regardless, we want to thank you for being here. We know your time is valuable, and we will do our best to make sure these sessions continue to be valuable to you. The past 2 weeks, we have had guest speakers with Dr. Carl Slater from the University of Warwick and Dr. John Lippold from the Ohio State University. I want to again thank them for their contributions. In the coming weeks, we will continue to feature guest speakers who will present their research and the role that the Gleeble has played in their projects. If you or your team are interested in presenting at a future webinar, please let me know. As always, our goal will be to keep this webinar to 1 hour or less. Given that this is a re-recording, we will not have live Q&A at the conclusion of the presentation. You will be able to find a link to this video as well as videos of past webinars by going to our website, gleeble.com, and clicking on the resources link in the top navigation bar. And then if you click on webinars, you'll come to a page and you can view past webinars and sign up for future webinars. Next week's webinar will be a little bit different. We'll have a different format. Over the past 10 weeks, we have had a lot of great feedback and questions that we haven't been able to address in the Q&A. We will sort through those questions and themes and talk through them. So there won't be an overarching theme of the session, and we may bounce around a little bit. Some of the content may be a review for our very experienced Gleeble users. However, I'm confident that even our most tenured Gleeblers out there will find the webinar informative and may generate new ideas and drive new innovation. This week, I'm excited to hear from Dr. Wayne Chen, one of DSI's metallurgists and head of DSI's China offices in Shanghai and Beijing. Dr. Chen started working with the Gleeble in 1500 in 1986 and studied at the University of Science and Technology, Beijing, and then at the University of British Columbia in Canada. After his PhD, Dr. Chen came to work at DSI in the mid-1990s and worked extensively in R&D and contract testing. And as I've said in the past, we don't have data to back this up, but I expect that during a 10-year period here at DSI, Dr. Chen probably ran more Gleeble tests than anyone else in the world. Since then, Dr. Chen has helped DSI open our China offices and continues to be a technical resource to DSI and our customers in China and the rest of the world. Dr. Chen will be presenting today on casting applications and semi-solid processing. Wayne, thank you for taking the time to prepare this presentation. You should have control. I'll hand this over to you.
Thank you, Dan, very much. Hello, everybody. It's a great pleasure to have this opportunity to share some of my experience in using Gleeble on casting and semi-solid processing simulation. Okay, so today I'm going to cover 4 topics in terms of industrial casting and semi processing. And then I will present some of the testing technique or simulation techniques using the Gleeble on casting and semi-solid processing. And after that, I will make kind of 2 applications using the Gleeble to develop the castability map and the CCDR process simulation, which is really continuous casting and the direct rolling. So let's talk a little bit about the industrial casting technology development first. Okay, we know that the casting is a very important part of the steel making process, and in fact, continuous casting is one of the very few technologies that really shape the steel processing industry. As we know now, the steel product is so really cheap in a way, and that's really partly contribute of the development of the continuous casting technology. And the Gleeble can really simulate the whole process, not just the casting. But today we are going to focus on the casting part of the process. And before that, going to further, we'll talk a little about the industry history on the casting. Everybody knows about it, but I want to just repeat here a little bit. Casting really in the industry starting from 1947 up to like 74, over the almost like 20-30 years. It's really focusing on the mold casting and the blooming, which means you have to break the ingot to start the rolling after that. And then from 74 to like 89, in about like 25, 10, 15 years, continuous casting really stopped. But then at that time, they are really not integrated. Still needed to kind of separate the casting, rolling is rolling, right? So that's why I didn't say the direct rolling, still say hard rolling. But since like late 1980s, until now, the continuous casting and direct rolling become really a major industrial trend now for all the steel producers in the world to produce steels, specifically for strip steels. There are lots of technology coming out, like CSP and the CPR, and lots of casting caster manufacturer who develop mainly good thin slab or strip casting technology, such as Daniel, CMAG and Shimag, all these companies, they have done lots of it. And most of the world's steel producers are using this technology to produce steels everywhere. And again, if we casting, again, as I said, it's just part of the steel processing. So you have to really combine the industrial hard rolling as well. But before that, we have a kind of, hard strip manufacturing or casting technologies developed from thin slab to direct thick strip casting to thin strip casting. But all these things, in order to make the subsequent rolling even more efficient, people are using semi-solid processing as well. In other words, you are deforming the steel billet, no matter how thick it is, while this core is still in a liquid zone. So we call it semi-solid processing. Okay, now, so here is an example, some examples of the really CCDR process. From things conventional, we know it's a really slab. Normally the thickness will be around like a 250 millimeter, and then the continuous rolling to 1.5 millimeter to 25 millimeter thick. But when the technology develops, especially when the thin slab continuous casting technology developed, the length of the production flow becomes very short, from like half kilometers down to like even 100 millimeters. So this development not only make the steel casting much more efficient or steel rolling much more efficient, the key is also the investment is much more less than conventional ones. So there are lots of technology out there that are using. But again, one thing is very important, that no matter what technology they're going to use, as far as I know, I might be wrong, but as far as I know, no technology can produce all the steels in the world yet. So they are still limited. And that is why that we needed to use the Gleeble to study the continuous casting and the rolling to make, the cast capability even more and more. Specifically, if we are going to develop new steel, so you need to use the simulator in the lab to study before we go to production trial. And this figure actually is the showing of the dendritic size, crystal size, in a different thickness of the slab, from like 500 millimeter thick to down to like 1 millimeter or 1.5 millimeter. But you can see, when the thickness is become bigger, the secondary dendrite arm spacing is become bigger too. And vice versa, when the thickness becomes like a 1 millimeter or a little more, then the structure is very fine. And actually, when for thin strip casting, the cooling rate you will see in the real production flow could be up to like 1,000 degrees C per second. And that is very important to simulate in the Gleeble. And the Gleeble, we know we can quench as high as even 10,000 degrees C. So Gleeble again give us a lot of capability to start all the casting and the direct rolling process. And this one shows the arm, secondary arm spacing distance, as a function of the thickness. So that's not really something new, but we all know. So we talk about a casting, and we talk about a continuous casting and the direct rolling. The key here is really, if we want to do continuous casting and the direct rolling, we got to make defects-free billet. If you have lots of defects on the surface, no matter it's in the corner or the edge or the longitudinal or transverse, it's not going to make you direct loading because you cannot roll the defects into the steel strips, right? So in conventional way is you have a frame, treating, but that's not the way to do continuous casting and direct loading. So producing defects-free castability is the key to do the CCDR. But the question is how we can achieve defect-free casted slabs or thin strips for direct loading after that. So that is why that the casting simulation technique is becoming very important. So in the next few slides, I'm going to show you some of the casting simulation techniques using the Gleeble. I hope that will be helpful to our researchers to use. And the first one is what we call is flat sample casting, because slab or thin strip casting, it's all rectangular. So we have developed a crucible that is very simple, just in the metal screen, and you put pieces of insulators, and at the bottom, and you put a quartz plate. So that one you can put a thermocut at the edge, and then heat it to about whatever temperature you want to get it fully melted, and then you control solidification. And then later on, you can either pull it to check the microstructure or micro defects, and then you can even machine the sample out of it to do the deformation. And this can be thick, can be thin, up to whatever the sample that you have. So it's pretty convenient and very economical too. Okay, and this is a very good example of the casting process simulation. We actually in this testing we use a pre-bend specimen. Okay, so when you use a crucible that I just mentioned to melting and solidifying, and then after that you can pour a little bit to simulate the unbending or bending process in the casting process, right? At a certain strain rate that you see or in the range that you want to study in the casting process. And then you can also use the quenching spray head to simulate the secondary cooling that you see in the real casting process. And as I said, after all the simulation, you can check the microstructure, you can check it to see if there is any defect. You can even cut samples out to do some mechanical or ductility testing. Okay. And but the most popular way that our Gleeble users have been using is really this testing technique. I would rather really call it as a Dr. Suzuki methodology, because this methodology was developed at the Nippon Steel in early 1980s, who used really a 10mm diameter bar, and he used a quartz tube to slide onto the cylindrical sample. And we know the quartz softening point is more than 1500 C, right? So you can really, for steels, most of the steels, you can simply just melt it to simulate the steel in the mode, and then you can just control solidification to simulate the casting cooling rate to generate the kind of dendrite you will see, and then you simulate the unbending process and a further subsequent to the hard rolling process by doing the hard ductility test to measure the reduction area. That way you will know this steel and these kind of casting and the solidification and the unbending, bending, unbending, or even the rolling, see at the different temperature what kind of ductility you have, because after all, it is ductility really affecting the defects, right? Everything is really material ductility. And of course, you have to have a stress. If there is no stress, then you will not have any cracks too. So lots of things you have to study using this kind of testing in terms of stress, in both the mechanical stress that you will see in the alignment roll, backing up a roll, and also the thermal stress you might be generated during the thermal gradient solidification. So controlling of the thermal gradient, control of the cooling rate, control of the solidification is very important. So this is a very popular technique that people are using. I would say every steel manufacturer who has a Gleeble using this technology to develop a kind of castability for all kinds of steels, even those new ones they are developing. I will talk about the castability method later, but for this testing technique alone, I want to share some of my experience with you guys now, because after all, this test is not that easy because it's melting. When you're dealing liquid of steels or metals, it's for some of the beginners, it's kind of nervous. But again, we have been using this for almost like 30 years now, as you realize. So it's not really a big, but still, there are some trick that you need to be aware so you can make your test, it's kind of routine test. So the key here is this. Okay, firstly, before melting, I would definitely suggest you to slow down the heating rate, because otherwise the control the liquid will be tough, right? As you can see, we have a lots of holding time. You can manually adjust the melting temperature or casting temperature, and then you can control solidification. But there are some things that I want to mention here. Firstly, as I mentioned, that we use the quartz tube, so the size of the quartz tube is very important. I'm sorry, because we know that if you do not select the right inside diameter of the quartz tube, then this quartz might break if it's expanded too much. So a rule of thumb is, if you know your steel the thermal expansion coefficient, with the phase transformation, you trying to estimate what is the final diameter that you would have at the the kind of melting point that you will see. So the inside diameter of the quartz has to be a little bit kind of bigger than that. Otherwise, you would break the quartz, because quartz is very brittle. Okay. And then the second thing is, as I mentioned before, that no matter what you do, when you have a metal, you have a thermal gradient from the surface to the center, right? Even though where the resistivity actually is, if you control where it's isothermal in a vertical plane. But again, you still need to minimize the radiation and the convection heat loss. Because if you do have a thermal gradient from the surface to the center, you might end up with this kind of hole after solidification, as you have seen from the ingot casting. You have some holes at the center of the ingot because of the thermal gradient you see. And that's the same for this kind of testing. So one way to minimize this thermal gradient is use a thermal sleeve around the quartz tube to minimize the radiation and the convection. So that way the temperature you measure the surface will be equal to the center. That way, whatever you measured is, you see in the melting zone. And also, when we insert a kind of thermocouple in the liquid zone, no matter it's a matter of water, let's say, it's very hard to have the thermocouple stay in the liquid, right? So that is very important. My experience is that you would need to apply a kind of compression stress onto the thermocouple joint. That way, when the thermocouple is, when the sample is melted, thermocouple will not be detached automatically, because you don't want to waste the test, right? So that's one experience that you would do. You could do it easily, because you can apply, after you put the thermocouple onto the juncture, you can just apply compression from the thermocouple. That's easy. But of course, there is another way that you can make it even easier. That is use a cement. We provide a cement to every Gleeble users. What you do is, you mix the cement with the water to make a kind of, mushy thing. And then you can cover this cement, the whole slot of the quartz tube. Okay. But you need to get rid of the water or moisture within the cement before you do the testing. So the way you could do is just heat the sample manually to, let's say, 100 plus degrees C until the water is evaporated, so the cement become solid. So there are two advantages of that. One, the cement will hold the thermocouple even when the sample is liquid. And secondly, because the cement has covered the whole slot of the quartz tube, even though there is some kind of stirring in the liquid, the metal will will not jump out of the slot. As some of you might have seen this kind of thing, but with the cover of the cement, this is not going to happen. So it'll make the test a little bit easier, and that way, you know, the test will be much more kind of easier. But of course, as you can see the photo here, we needed to insert this what we call the magnetic field guide at the back of the pocket jaw to minimize the magnetic stirring, because we know that we are heating space by electric current, like AC current. So when you have a current, you have a magnetic field. So we have a guide developed for that to minimize the stirring, so make the liquid metal in the most soil, you know, quiet. Not like the one in the molding, you probably want to kind of stir it to make it uniform. But here, I mean, as discussed, the structure you started with is uniform, so you don't really want to kind of make it stirring too much to destroy your sample. So these are the tricks I would hope that it will be helpful when you do this kind of melting solidification test. Okay, so now I will explain a little more details how to use this technique to develop a castability map, because after all, you need to tell your cast operator to how to cast your steels, no matter if it's the current one or the one you developed it, newly developed. I mean, a new alloy developer is always the race that every steel manufacturer is trying to win. So for all the new steels, you needed to develop this to make the casting much more easier, instead of wasting of time and the cost, because we know the plunge hire is too expensive. Lots of experience has shown that, you know, one plunge hire plug can save two Gleebles. Okay, so let's come back to the test methodology using this Suzuki method. What I would say, normally you could use this kind of methodology to do that. This left one is really to simulate the casting and the directed rolling. So what we do is you heat the specimen up until melting, as I just mentioned, all right, and then you control solidification to a certain temperature, whatever it's in during the casting temperature region or during the rolling region. You can do all type of testing to measure the reduction area, the ductility, and then you can also do at the different, soaking time, strain rate, all these factors you can put into consideration. That way, then you can have a ductility versus lots of factors in terms of temperature, strain rate, holding time, and all that. So that is the testing method, as I said, for using the Suzuki method. And the second one is to simulate really the hard charging. So we do still the casting, melting, and the solidification, but we cool the sample down to a certain temperature before the billet goes into the recharge furnace, as we do, right? So that's why we kind of cool down to a certain temperature and reheat it to another temperature, right? And actually in some of the CSP mills, they have a tunnel furnace. They are reheating either the slab, the edge of the slab, or the slab itself. Doing so also. So you can use this way to simulate whatever you've seen. And actually, I personally have also run a kind of environment in the tunnel furnace, because we know in the tunnel furnace you have nitrogen, you have a CO2, you have CO, you have oxygen, you have some other element as well. So as long as you know the composition of the environment in the tunnel furnace or recharging furnace, you can charge into your Gleeble chamber to simulate the environment your steel slab is experiencing. That's fine too. But here the right one, why people will think, why do you need to do this test? That is very important, because for every this kind of testing, we are doing the control casting, solidification, and hard ductility. You need to have kind of base results or reference results to do the references. So we call this test, it's called unheating test, which means you cut a sample out of a deformed structure, right? Or either rolled or forged, and you heat it to whatever temperature range that you want to study, casting temperature range and the rolling temperature range. You do the same temperature range hard ductility test as you want to see, stimulate either the CCDR or CC recharging, right? And by this design, you can know how bad or this casting ductility is. We all know the material ductility will become very bad when it's heated. And actually, the fact is the higher the peak temperature, the worse the ductility is. So melting, of course, is the worst. That is why the melting is so important. So by doing all this kind of testing, you will generate what we call the hot ductility curve, like this. Okay, and this one is very specific to and steel. What they do at the Nippon Steel, it's called aluminum cured steel. Okay, so this is one of the examples of their ductility curve at a different temperature at a certain specific strain rate and holding temperature. Okay, so you see there are 3 low ductility regions, what we call 1, 2, 3. And if you see the low ductility, you want to know why. I mean, you only know the origin of the low ductility, then you can improve it. So at the Nippon Steel, they use SEM, of course. I always say the Gleeble is the bullet making machine, and SEM is just the machine that to take the Gleeble sample as a bullet. Without a bullet, the machine gun or the the SEM is useless in certain way, right? So Gleeble is really can generate lots of samples for your SEM because it's even more useful. So to study the origin of the low ductility, you need to check the fracture surface, right? So by examining the fracture surface, you know why there is a low ductility. And for this example, it's very, I mean, now it's very easy, but they found out for low ductility region 1, it's because it's near NST, near stress temperature. So the ductility is very low if your thermal stress or mechanical stress in the casting has exceeded the stress that the material can stand, you will have crack. So that is why the smooth, very great alignment of the rolls, casting rolls is very important. Okay, but not enough, because the thermal stress generated by thermal gradient is very important. When I was a PhD student at the UBC, I'm lucky enough that I was working for Dr. Keith Bonham, who was considered a pioneer, one of the pioneers in the steel casting in the world at that time. And he has spent like a tremendous of time to study how to design the mold to control the thickness of the shear thickness of the steel. Because if you don't control the thickness evenly, then you generate thermal stress. And then when you have a thermal stress, I'm assured that you will have cracks. And the biggest challenge he told me is we are talking about the protective steel. Because we know that at that type of steel, the carbon content is normally from 0.9%, 0.09% to 0.12%. The shrinkage from liquid to solid is huge, or over let's say the maximum. And if you don't control well, the gap between the shear and the mold is so big, and then you would generate lots of uneven shear thickness. And as long as you have uneven shear thickness, you would have a problem. Dr. Keith was once even say, he said, Chen, if you can solve this, practical steel casting problem, you will be a world-known research. Of course, I didn't have the opportunity to do so, but again, I hope our research using the Gleeble can really study this on the Gleeble to get rid of this longitudinal cracking with this protective steel. Because in the world, I'm telling you now, not everybody can really cast this protective steels yet. Some of them they could, but not everybody could. Again, so this Gleeble is very important. So coming back to the low ductility region 2, I mean, they found easily from the SEM, it's the inclusion, non-metallic inclusion that caused the problem, because it's segregated into the grain boundaries. So when you have deformation in there, it's going to crack, right? So, and then that is why now it's become very kind of usual now, but that time it's not. The clean cut steel is the goal, and it's still the goal. I mean, you got to make this your steel much cleaner, because if it's not clean, you have a problem. We have 5 bad elements like phosphorus, oxygen, sulfur, all these. You need to make all these elements as minimal as possible. So that's why we have so much of the cleaning steel technology, radish, these kind of vacuum degassing, all these technology to make the steel pure, cleaner. That way you can make the ductility bigger and better to avoid all these cracking you see. And the third low ductility is associated with the phase transformation from austenite to ferrite. When for this steel, actually they found that ferrite was precipitated at the austenite grain boundaries, and at the same temperature when the ferrite was formed, actually the strength of the ferrite is softer than austenite. So when you do the deforming, no matter how big it is, strength will be concentrated at the grain boundaries, and you might get cracked, and that's how the low ductility is. So in order to reduce this low ductility or get rid of these low ductility, they make the steel cleaner, and they trying to avoid the low ductility. For the first one, it's tough because you have to go from high temperature, down to low temperature. So the NST is always there. And as I said, the only way is to minimize the stress, no matter it's a mechanical stress or thermal stress. But the thermal stress is more important because mechanical, I mean, you just ask for those manufacturers, Danieli, hey, give me a smooth alignment of rhombus. Don't give me any mechanical stress in the castability, right? But in thermal stress, it's really the motor control, motor design, and really solidification control. So the way in this castability you will see is that's a temperature versus really time. So they plot these 3 low ductility regions as a contour in this map. We call it as a really castability map. So what they see is this. In their original casting cooling rate, it's about like a 20 C per second, as you can see here. And this castability actually going through all these 3 low ductility. So no wonder their castability has so much of the cracks. Actually, at that fact time is they have 45% of the slab has to be frame treated to get the surface defect. It's wasting the metal, it's wasting the energy, it's wasting the time, and there is no way you can do continuous casting anymore because the temperature is going down, right? So they have to minimize the crack. So the way they did it is by doing 18 months of testing using this technology. They developed this. So the way they do is instead of cooling that fast, they're slowing down the cooling in their secondary cooling region. Okay, so when the build trying to get into this like almost 1200, 1100 degrees C, they reduce the cooling rate again. So it's not going to get this poor ductility region. And then when the surface temperature of the slab go down to around like 900 degrees C, before it goes to the third low ductility region from 600 to 900, as you can see from here, they simply stop cooling. So then the surface temperature will rebound because the inside temperature is still hotter, right? So this way they let the slab avoid the low ductility 2 and 3, and they minimize the thermal stress or mechanical stress in the region 1. What I'm telling you is their surface treatment rate dropped from 45% down to less than 5%, which makes the CCDR a reality. Okay, so now, as I say, all the new steel they are developing, you got to develop a castability map before you can tell your caster operator how to cast, because the speed is really a strain rate in terms of the Gleeble simulation, cooling rate, solidification rate. It's all so important. When to unbending, and it's so important. So again, this technology is very important. I hope this will be useful for all your new steel development and casting. And now I'm going to talk a little about the continuous casting directly, because after all, the metal has to process it to become the final product our steel customers can use. Okay, so from this figure, you can see, there is a history of this really casting and rolling. From the right, that's the older one, early, probably like in 1940s, 1970s. People do cold charging. In other words, you cast it, right, and until cold, and you reheat it, through the walking beam furnace. And later on, it becomes like a short term. It's called a hot charging, right, to save some energy, to save some time, right. And then we got a direct hot charge, just like the second, schematic, testing scheme as I just showed in the previous slide. And now, as we all know, almost everybody is using CCDR, so this one, to produce all kinds of thickness of the strips using hot strip mill, no matter if it's 5 stands or 7 stands, depending on the thickness that you are going to produce. Okay, so now fortunately DSI has developed a CCDR simulator. We call it HDS V40. HDS is really standing for hot deformation system. V40 is really vertical 40-ton machine. We are using a very large sample, as you can see from here. It is a 10 millimeter, normal specimen is 10 millimeter thick by 50 millimeter wide and 250 millimeter long, depending on the free span that you want to set. And then, as I said, you use our crucible, which is really nice. You can bend it to a shape that you want, to do the testing. Very economic, very cheap, I would say. And then you can heat it to whatever temperature you want. And I'll show you a video to simulate the CCDR plus in the Gleeble HDS V40. Okay, so you see it's heating up a little bit slow, but you will see a molding zone in the center. Okay, and you will even some a gas kind of popping up, and I see the center zone, molding zone is generating now gradually. You can get a formatted without crucible, because as long as it's not in the vacuum is not the environment I will command, right? Normally is inert gas will be better. So it's kind of fully melted. You could, because you can see it's kind of bubbling in the center. And then you control the solidification, right, as you see, and then you can do the direct rolling right afterwards, as you can see here, because it's all in situ simulation of the CCDR process. You can do as many hits as you want, right? 1, 2, 3, 4, 5, whatever you want. It's not a problem. We can control the temperature. We can control the strain plus slightly. We can control the strain rate, and we can control interpass time, as you see in your real pressure flow. And this photo we show deliberately to show the kind of liquid. And we kind of deformed while the specimen is still in the semi-solid region. So you can see some of the mushy zone out of this. But as I'll show you, you can deform at any temperature you want, any time of strain rate or strain you want. You don't want to really kind of make it mushy, right? But I propose to do this because you want to show the HDS can do whatever you want to simulate, right? And after that, I want to show some of the microstructure of the melting and the solidification with the two kind of cutting. One, what I call the flat section, parallel to the surface, and then a longitudinal, vertical, like we call the long section. And then we will examine this microstructure from 1, 2, 3, 4, 5, from the solid to the S-cast structure. And here you can see in the long section from 1 to 3, like 1, it's a solid. It's about like 1,300 seats, reed and a solid. We see it's a normal Weatherman stent type of structure, but we have preserved non-metallic inclusions, because this is the one to show you why it's changing at a different temperature, like the one you see in the zone 2, right? And you see some of the non-metallic inclusion has been become fragmented, right? Because of the machine zone, semi-solid zone. And in the full melted zone, we call it zone 3, we see dominant the spherical inclusions along the boundary of the columnar dendrite. So in other words, we can generate columnar microstructure or as a custom microstructure. And if you want to see from the flex section A, after the deformation, right? Because section A is the zone 5 is the deformed zone. We can, again, it's a very common ferrite product structure. And if you want to see in more detail, you see ferrite, laminar layer ferrite there, right? And actually, in most of the S-cast deforming zone, we see Baynard as a second phase in all these zones. Like the zone 1, even we see the second phase of the Baynard structure. Okay. So again, as I said, this this simulator can simulate all kinds of casting procedures. This machine can actually, as a feature, we can shift the specimen longitudinally. In other words, you don't have to deform in the melting zone. You can really shift the sample sidewise to deform in a different zone. That's possible. But I want to make a case study for a steel with low carbon steel, 0.07 carbon with 1.5 manganese, but my alkali with vanadium and niobium, to do some of the deformation simulation, casting deformation simulation to see the microstructure and the flow stress. One is we'll heat up to 1250 with 2 heat at the 0.35 at the 1150 and the 0.55 strain at the 1000 C. And the second one will heat the same temperature up to 1320 with the same deformation, 2 deformation. And the third one heat up to the 1470 to melt it at the sample and do just 1 hit at the 1150 and 0.35 strain. So we will cut the specimen like crosswise. We call it middle zone, middle plane, and the longitudinal direction to see the microstructure. And you can see, okay, in the crystal after melting and the solidification, we see columnar structure by ferrite segregated along the grain boundaries. Okay. So you see the grain size of the columni, dendrite grain size. And if you want to see the inside structure, within the dendrite grains, we actually see some kind of, rib-like structure. And if we cut specimen along the middle plane, we actually see a dendrite grain size of up to like 2 millimeters, and which is very close to the dendrite grain size that we see in the real thin slab casting process, about a 25 millimeter thick slab casting. So again, the HDS is really comparable to what you see in the real casting process. And here is really the flow stress, curve that we measured at the different three different peak temperatures. What we can see is, of course, you can do multiple heat, about 5, 7, so no problem. With because the HDS has also a feature of the hydroage. You can control the strain rate, temperature intervals very well. And here, what we see is, see the finer the grain we see, the larger the flow stress you observe. Like you see the low flow stress at the 1470 melt zone. We deform at the same temperature. The only difference is the grain size. So the finer the grain size, the larger the flow stress you get. The same for the 1000 C deformation, heat at the 1230 and the 1250. Okay, so that's why we need to make sure the peak temperature that we simulated, because it's all affected the deformation resistance that you will see during deformation. And these are the photos that Microstructure photos you see for the process 2, that at the different two temperature, different strengths. D is the deformation zone, 1 is the kind of the non-deformation zone, and the microstructure. And you can see it's it looks at the structure after deformation. The same for process 3 with S-cast and the solidified deformation structure. So these are the things that normal that all the Gleeble can do it, to check the microstructure, because after all, it is a microstructure to decide what the mechanical problem is. So CCT again is also very important to measure. We could actually measure the CCT on the HDS V40 as well. Okay, so these are the example of the the case study, and I want to make a conclusion for this case study. I mentioned already, but I want to summarize it. Firstly is the HDS V40 really can simulate the true melting and solidification situation that you see in your real process. Okay, and then followed by a multiple-step hot rolling process in your as you see in your project flow, and also the reliability of this process, simulation process, is very positively verified by the mechanical metallographic observation, as we can see, using the non-metallic inclusions, right? And also, as I just mentioned, that the columnar grain size that we achieved using this methodology is equivalent or is comparable to what we see in the industrial thin slab condenser casting process. Okay, and before I finish, I want to really propose a SICO procedure, because SICO procedure is really good testing procedure that all our Gleeble could try, because it can be applied in so many different applications, not only for just correct stability study. We can optimize the process as some of you have seen to optimize the crankshaft process, but here you can use this SICO procedure to test the CCDI process as well. So the way I would propose to do is that you use the crucible to melt the specimen to control the solidification process, and then you just simply compress the specimen to a certain temperature, to a certain strain rate, and you can either measure the mechanical property afterwards, or you can check the microstructure at the different testing condition, and also you can measure the onset of the cracking by measuring log D over D as the ductility. And using DIC, digital image correlation technique, is perfect for me to check the onset of crack strain. So I personally, honestly, have not really used the SICO to simulate the CCDI yet, but it's a very straightforward. Some of users, if you are interested, you want to tell it, and you're welcome to try it. And if you have any problem, you're welcome to contact DSI, anybody. We will be more than happy to help you. And here is the contact information that you can go after, either for service or parts or other kind of research, the subject that you want to do. We always will be very happy to work with Gleeble researchers, all the kinds of research project that you have. Even though nobody has done it, we'll be happy to work with you to develop the testing technique that will be happy to share for the rest of the Gleeble users. Okay, thank you very much for your attention. And with the pandemic still going on, I hope everybody stay safe and be well. And hopefully this vaccine will be out very soon, so everybody will be getting normal, even though it's a new normal. Again, thank you very much.
Wayne, thank you very much for preparing this presentation and sharing this information. We really do appreciate it. As Wayne mentioned, if you do have technical questions, please do reach out to us. The best way to do that is, as Wayne mentioned, on our website, there is the customer service portal. So if you go to Gleeble.com and then I believe there's the resources tab, drop down to customer service portal. I've mentioned this at a few of the webinars. This really is the best way to get a hold of our service team. Once you're in there, you'll be able to search a knowledge base, which is very valuable, as well as create a support ticket. It really is a great way to connect with the team. If you have any questions about how Gleeble can support your research, please email me and I'll connect you with the application expert to help you find the right solution. My email address is dan.quigley@gleeble.com. Thank you everyone for joining us. And as Wayne mentioned, please do stay safe and healthy and have a great day.
Thank you. Bye-bye.